All right. This talk is, thanks Vikrant for covering the benchmark data. So this talk is basically we are going to cover the logical and physical architecture. So we have 3 speakers. So myself, Reddy, I'll start off very quickly, and then Vikrant is going to cover the mapping of logical architecture to Kubernetes. And then the remaining talk is actually Soman is going to cover the physical architecture part. So the logical architecture we actually decomposed into 2 basic constructs. This is probably familiar to most of you. So when we look at the memory hierarchy, we look at this into 2 different groupings. One is the near memory. Near memory is anything that is actually closer to the CPU. This is essentially the host DRAM, whether it is on the local node or the remote node, or it could be high bandwidth memory in the GPU. So we look at that as a near memory. Far memory is anything that is actually driven, which has the load store semantics, but essentially connected over the CXL type of fabric or memory type of fabric, and it has a higher latency compared to near memory. So that's the way we are segregating in the logical architecture. And then last but not least, there is also block storage that forms the hierarchy when we look at NVM over CXL type of media later on. This is the work that we have done in the CMS sub-project. So I won't go into the details. This is actually captured in the white paper. So at the highest level, there is the host that is actually consuming the memory, that has the firmware that essentially knows how to enumerate all the devices that are actually connected. And then, of course, there is operating system and VMM that essentially consume the memory. Like Vikrant said, it could be a logical, memory-only NUMA domain as an example. Then you essentially have the management controller. So we didn't want to call this as the baseboard management controller and make that as an implementation artifact. So in the logical architecture, you see that as a management controller. Primarily, the management controller is there to do the out-of-band manageability. So you can see that there is an agent that is actually connected to the data center fabric manager. So you have a direct attached CXL memory buffer in the architecture. Then you also have multi-headed, and then the fabric-based. And then there is the CXL over alternate transport as well. So our focus is to essentially include all those elements in the logical architecture, as well as ensure that there are solution architectures around them. Last but not least, there is also data center memory fabric manager that stitches all these pieces together and works with the orchestrator to provision, deprovision the memory. So that's the logical architecture in the white paper. You can actually take a look at the white paper for details. With that, I will hand it over to Vikrant, who will talk about the mapping of this architecture to the Kubernetes.
Switch the. Hello. All right. Okay, so I'll talk about how we use the logical architecture that Reddy just flashed. I'll just talk about how we are using that, and I guess the takeaway for me in this slide it's the whole hardware software philosophy and how we are embracing that. And I know Siyama keeps talking about it on every call. And this is sort of bringing all of that together. Like when I presented the logical architecture diagram to a couple of engineers on the Kubernetes team, like they immediately had feedback on and which are the top 2 bullets, that if we really have to consume pooled memory or any sort of CXL device, we need to make sure that our service owners do not know that it's a special type of memory. And that was the driving principle or guiding principle around which we built this particular topology. Then I also had help from SK Hynix. The team at SK Hynix also done some prototyping using Kubernetes. Reached out to them, saw how they had done this last year when they had presented at FMS. So all this really helped narrow down sort of this workflow that I'm putting together. And again, this is open for discussion. This is a first attempt. But really, the hardware-software design is key if you have to make this container use case successful using pooled memory. one of the other driving factors or the requirements for our Kubernetes team was they want to use the existing semantics within Kubernetes. So CPU set.mem is essential. They don't want any sort of flags that say that it's a special pool memory or it's a local DDR memory, because that will be a big tax for us to consider pool memory within our infrastructure. So given that, the way I was thinking about this particular topology was you have this memory appliance that registers itself with the Kubernetes master. And this is drawing inspiration from how the storage vendors have done it, where it shows up as a appliance or a object class within the Kubernetes master and allows you to essentially create slices of memory within using the knobs in the Kubernetes master. So all these will be bundled and managed and orchestrated by the Kubernetes master. So when you have a pod spec or a config file that is submitted by our service owners, and they just ask for memory, it transparently is orchestrated by the Kubernetes master, where it looks at all the topology map or the topology manager that shows the zero-core NUMA domain memory as well as the existing direct attached memory, and figures out how many slices it needs to hot plug into the host that can support the specific pod spec. So this is the high-level idea, and then of course there are the internals that have already been ratified within CXL, like the hot plug process, and how it shows up in the Linux kernel as a zero-core NUMA. All those are already built out, and Reddy, of course, helped me on that as well. So this is where we are, and I'm hoping that as time goes by, we have some more clear definitions and APIs coming from the data center management API workstream that will allow us to embed those within the Kubernetes open source code. I think that is it. Yeah.
Okay, very good. So far we talked about logical concepts and aspects and how AI or large memory databases need more memory or larger number of devices, and we believe CXL is a way to interconnect them. And then we are here at OCP. OCP is the place that we bring technologies into real systems. So today I talk about a little bit of the system aspects of these concepts. A little crash course on CXL as a reminder. If you remember, CXL protocol is laying on the physical layer of PCIe. That makes it easier for initiating any kind of programming that you used to do with PCIe. But then on top of it, it adds two new protocols, the .cache and .mem, that provides a better method of moving data between accelerators and host. When we combine them all, then we get into a converged memory. That's where the accelerators and host can share memory regions for efficient data movement. So basically, this converged memory is key for easier programming for software developers and more efficient data movement. So if you remember, we have three types of CXL memory devices: type 1, type 2, type 3. Type 1 is the one that's basically an accelerator. NIC could be an accelerator, as an example. Uses .cache. .mem is used by the type 3 device. That's a memory expander. And the device that can do both of them is type 2. CXL devices receive .mem. CXL accelerators initiate .cache cycles, and CPUs initiate .mem cycles. So CXL 2.0, as a recap again, provided a few enhancements. It provided memory pooling. It increased the number of devices you could connect to one port using one layer of switches. Provided security through IDE, and to support storage, it provided global persistent flush. So that was CXL 2.0. But everybody is asking for better connectivity and removing all kinds of bottleneck. CXL 3.0 came in and provided other mechanisms, streamlined peer-to-peer transfers, a CXL device connecting to a memory device or a storage device through a switch to remove bottlenecks. We don't have to go through the host anymore These can directly talk to each other. To support that, memory HDMDB was generated. We created and supported unordered I/O, and to support a memory region that can be shared amongst multiple hosts, we had to invent a back invalidation flows, and that's a new channel. So CXL 3.0 supported all those features. These created new capabilities for us. So, for example, memory can now be shared amongst multiple hosts. A memory region can be mapped to more than one host, and they can, in fact, take advantage of that shared memory region for host-to-host communication. A minute ago, I talked about peer-to-peer communication through the switch. In this model, through the shared memory, hosts can even share tokens or semaphores or move data across. When we put them all together, then we can create a system that provides disaggregated computing. Memory is separate from where the processing element is. At the same time, then we need to reverse the process and aggregate them all. So composable systems is important, and that's the main theme of the talk all day today. Composable memory systems out of disaggregated components. Disaggregated components can be through switches, as an example. So when we do all of those, then CXL allows a very large fabric. This is an example. You have a rack. In this rack, you have multiple nodes, multiple chassis. And one chassis can take on the function of a memory appliance, another one storage appliance, another one might be a switch appliance. And the data can move easily through multiple switches and create the same software environment for developers. So composable memory architecture then is a new paradigm that we can enable through CXL, and that's good for HPC, AI/ML, and large databases. So traditionally, we have a server composed of a compute element, CPU, memory, networking devices, and storage. With CXL, we can add more memory, more devices, 1, 2, or many, based on the number of links that its processor has. We can enable emerging memory technologies independent of what the CPU can do. Nowadays, we can, in fact, have multi-port access to memory. With that, we can create memory pooling concepts and sharing devices. Silicon is on the floor. Go to the show floor. There are some good examples of some of these techniques. Now, our other systems we talked about, a memory device that has multiple ports, and a CPU that does have multiple ports can be put together to aggregate bandwidth. We did talk about CXL using PCIe for physical layer, and we're limited to the bit rate that CXL can provide. The PCIe can provide. However, with CXL, we can interleave multiple channels. You can aggregate the bandwidth of multiple channels. For example, if you use 4 by 16 CXL channels that are interleaved using CXL 3.0 running at 64 gigatransfers a second, you get to 1 terabyte a second of aggregate peak bandwidth. That is equivalent to what an HBM memory bus can do. So this is an example of how we can actually interconnect these. Individual devices can be connected through switches to create appliances. Now, we do have challenges. Interconnects is complex. Switches, we did talk about that, add power, latency, and complexity. Copper interconnect is bulky. And then availability, every time that we go to disaggregate compute, we have to be worried about. So the main concepts then will be, first, do no harm, put everything where they belong, and push the envelope, but retreat whenever it is too difficult. On the First, do no harm. That's the main theme of discussion here. We want software to feel comfortable that what we are presenting through composable system is the same as before. Putting things where they belong is the work that we're doing across OCP with partitioning systems in the right way. So we encourage all of us to build reference systems. Reference hardware system will allow software guys to come and work on it. And once software is defined on reference system, the following hardware system will follow that software reference, and therefore we perpetuate commonality forward. As an example, we can come up with a balanced architecture across memory, compute, and interconnect, and storage. It can be partitioned using a backbone. This is the backbone. This is an interconnect backbone that we need. Cable manufacturers, connector manufacturers can help us come up with one robust assembly for an interconnecting a number of CPUs, a number of memory for memory pooling and memory sharing. Photonics can come and help reduce the size and dimensions of these connectors and cables and increase the length of the reach that we can have. Putting it all together, chassis can be built using power and cooling and techniques that we already know. Use CXL for memory pooling and sharing, and the software concepts that Composable Memory Systems is talking about will create an integrated system. So we could have a system that is interconnected tightly within one ensemble, one locally disaggregated system. They can be connected through a fat pipe, basically, multiple systems using fat pipes. That's when we need more bandwidth. These fat pipes, the systems can be farther apart in a rack or maybe multiple racks. For all of that, we do need a number of software elements to come and help us, and a number of people are working on that. CXL Fabric Manager, any kind of a pre-boot environment that we need, drivers and benchmarking we talked about. All of those things put together creates an integrated system. So if we have a common software infrastructure, it creates the interoperability that we were talking about. So we all invite you to join us. Bring your challenges, bring your use cases, and within OCP we have a number of work groups and work streams that are attacking individual components of it. Extended connectivity is the work stream that is talking about how to cable these things together, how multiple chassis we might have. Composable Memory Systems, this track today, talks about software elements, benchmarking, how to manage these things. And DCMHS, modular hardware system subgroup, is the one that brings in hardware components aspects of that.
May have like maybe a minute if there are any questions. We can just do a quick Q&A and transition over to the next topic. Any questions for the presenters? Manoj, do you have a question?
I have a question
Oh my God.
about this group called CMS, what it's working on. What would be the next deliverable for this work?
Yeah, so the next deliverable will be just on the architecture specification, right? So the next deliverable will be essentially looking at the fabric side of the scope and then refine the architecture to include that. This includes the AI fabric as well. We don't have that very well covered in the initial spec, initial white paper, sorry.
One important piece, Manoj talked about, AI systems are requiring different system components. Some of them require more compute, some of them require more connectivity, some require more bandwidth for memory, some require more memory capacity. They're all true. One piece I will talk about this afternoon as part of a continuation of this is that fact. We as system suppliers, system architects, can specialize for different workloads. But you guys know these workloads change very fast. So another approach is to have a balanced system, a system that's modular, flexible, so that different use cases can land on the same hardware. That will help investment protection for a lot of people, for suppliers and for the consumers.
All right, thank you. We'll transition it over to the Kiran. Where do we have Kiran?